This is our second talk. We just gave a talk on deeper door exploiting the NIC chipset, where we talked about a chipset level backdoor that basically runs underneath the Indus and the TDI Windows networking components and talks directly to the NIC hardware. We showed that we were able to send and receive data through a couple of different firewalls, and we're able to even send out data once we had uninstalled the card from the Windows Device Manager. Nevertheless, our deeper door is still somewhat detectable running inside the OS. We had to, for example, hook an interrupt in order to intercept the frame arrival of packets. So deeper door is actually better suited to move it into a different kind of rootkit that can exist independently of the OS. So that's what we've done, and that's what the topic of our next talk is about, is a system management mode rootkit that we've developed. And we've integrated the deeper door functionality into our system management mode rootkit, which gives it even more stealth. So the functionality of our rootkit, it functions as a chipset level keylogger, and it exfiltrates the logged keystrokes out across the network using some of the ideas that we talked about in our last presentation. So rootkits can be classified as either OS independent rootkits or OS dependent rootkits. OS dependent rootkits have to make changes to either code or data structures in the OS in order to exert their control. In contrast, OS independent rootkits are capable of exerting control without making any visible changes in the host OS. So over the years that rootkits have existed, a bunch of different techniques of varying levels of difficulty and complexity have been developed. One of the earliest such techniques is this idea of hooking. Hooking can either involve changing operating system code. For example, we might hook a Windows API by replacing the first few bytes of the function with a jump to our rootkit code. So when any other application calls that API, we gain control first, and we can decide what we report back to the user. That would be an example like of inline hooking. We can also hook operating system data structures like the system service descriptor table by changing the pointers that point to various operating system services to point to our rootkit code instead. So when those services are called, the rootkit code is called first. Two examples of rootkits that use hooking primarily as their method of control are the Hacker Defender rootkit and the INTI rootkit developed by Greg Hoagland. A little bit more advanced technique is direct kernel object manipulation. Direct kernel object manipulation was talked about by Jamie Butler and was implemented in his FU rootkit. Basically, direct kernel object manipulation involves making changes to operating system data structures that are dynamic and that tend to change. Because if you have a data structure that is always the same and always contains a static value, then perhaps it's possible to hash it and to gain some idea of what the baseline value should be. But if that data structure is always changing, there's no way to obtain a reliable baseline. And the perfect example of this is the Windows process list. Windows maintains a linked list of process structures with one structure representing each running process on the system. So what the FU rootkit does is it goes out and it walks this list and locates the process block for the process that it wants to hide, and then just simply snips the linked list pointers and reconnects it around the hidden process. So next time the OS goes out and walks this list, it totally doesn't see this process because the pointers now point around it. Also, processes are constantly being created and destroyed, so it's almost impossible to establish a trusted baseline of what should be in that list at any given time. Therefore, direct kernel object manipulation is a more advanced and more stealthy technique than hooking usually, although it has more limited uses. It's also an OS-dependent technique since it operates on the OS data structures. Finally, virtual memory subversion. A couple years ago, I wrote a proof of concept rootkit called Shadow Walker. It exploits the Intel split TLB architecture to subvert the view of memory that is either seen by the OS or by other kernel code. However, I still had to make changes within the OS. I had to modify some of the paging structures. So therefore, there's still avenues of detection. So generally, these type of rootkits are detected by the fact that they do make changes to the OS. And there's usually some method of detecting these changes. A number of different tools have been developed for this purpose. One of them is the VICE tool. That was one of the first ones. VICE was developed by Jamie Butler to try to detect hooking activity and hooking behavior. So it goes out, for example, and walks the system service descriptor table and looks at all the pointers in that table and tries to see if any of them point outside loaded OS modules. So if those pointers don't point within the kernel, then that's a pretty strong heuristic that, that something's hooking them and that something could potentially be malicious. System Virginity Verifier was developed by Joanna Rakowska. It's another approach. Her tool operates as a sort of memory integrity checker for Windows system components. Then there was Rootkit Revealer, which uses what was termed a cross-view detection approach. Cross-view detection basically compares a low-level view of the system with a high-level view. And so it asks the question two different ways, one at the high level, one at the low level. And if the answer that comes back is different between the two, then that would indicate, possibly some suspicious behavior. So OS-independent rootkits don't make changes to the OS. Those type of rootkits include Blue Pill, which exploits the AMD virtualization extensions and was developed by Joanna Rakowska, as well as the Vitriol rootkit, which is the Intel version that exploits the Intel virtualization extensions. BIOS rootkits can also be thought of as OS-independent rootkits. John Heisman developed a proof of concept ACPI BIOS rootkit that he talked about at Black Hat a year or two ago. And then finally, SMM rootkits kind of represent another class of OS-independent rootkit. So OS-independent rootkit detection is a lot more difficult than OS-dependent rootkit detection. Detection methods tend to be more indirect. Like for hardware virtualization rootkits, some of the detections that have been proposed are like timing detections. So, you read the timestamp counter before and after a VM exit event. And if clock cycles were lost, then possibly, some code ran, during that VM exit and might indicate that you're actually executing in a virtual machine. Other timing detections have been suggested kind of along the same lines, using either cache or TLB discrepancies. And then finally, the memory footprint can be used if you know what you're looking for and you have a signature for it. And if the virtualization rootkit is not using memory virtualization to hide its memory footprint, then you may be able to detect it through a signature. BIOS rootkits, suggested detections include like preventing BIOS reflashing or requiring that the BIOS be signed. So what is system management mode? System management mode is one of 4 Intel processor modes. The 4 modes include real mode, protected mode, virtual 8086 mode, and system management mode. Real mode is the mode that legacy DOS ran in. It's a 16-bit mode environment. There is no real concept of memory protection or paging. Protected mode is the mode that your Windows operating system runs in. Protected mode has memory protection and also support for paging, as well as support for accessing 32-bit or 64-bit addresses. Virtual 8086 mode is kind of an obscure mode that was used at one point for trying to provide an environment for executing legacy real mode code in a protected mode environment. And then finally, system management mode, or SMM, is also kind of a legacy mode, which was used mostly for low-level hardware control, and it's actually still in use today, like on your laptops where you have power management. A lot of that power management is actually implemented through system management mode. So SMM can be used for power management, thermal regulation, or even like legacy device support. There's some usage for supporting like legacy PS2 devices, keyboard devices. The actual environment of system management mode is probably the most similar to real mode in the sense that SMM is a 16-bit mode environment. Although you can actually access the 32-bit flat address space if you use override prefixes. There's also no paging like real mode, and SMM is also non-preemptible. So if you're executing in system management mode, no other events on the processor can cause you to be interrupted. So you have exclusive use of the CPU. So why is SMM an attractive place for a rootkit? Well, probably the biggest reasons are the fact that SMM provides an isolated memory space and execution environment. And the space can be made invisible to code that's running in other processor modes, like Windows protected mode. SMM has no concept of protection. Inside SMM, you can access all physical memory, and you can execute all instructions, including privileged instructions. Another capability that you have in SMM is you have chipset level control over all peripheral hardware on the bus. You can also intercept interrupts without changing processor data structures like the IDT. And you can communicate directly with any kind of hardware on the PCI bus. So as it ends up, actually, most rootkit functionality that you would want can actually be implemented in SMM. So exploiting SMM is not totally a new idea. Duflo, another researcher, first discussed the idea of SMM-based malware. He actually demonstrated using SMM to escalate privilege on an OpenBSD system. His code modified a variable that determines the current privilege level to change that variable to make it appear, to make the system appear that it was operating with more privilege than it actually had. There's also 3 guys that recently wrote a FRAC article. It was entitled Using SMM for Other Purposes. It gives some more details on SMM and some thoughts about how to create stable SMM code. However, none of this previous work was really what you would call a rootkit. One of the most interesting aspects of SMM is the fact that you have unrestricted control over peripheral hardware at the chipset level. So we build on Duflo's work and the previous work to develop an SMM handler that has more rootkit-like functionality. We wanted to explore, what kind of capabilities might an actual rootkit have in SMM, and what would be the limitations of such code. So the functionality that we have currently in our SMM rootkit is keylogging functionality. This is about the lowest level keylogger that you can get short of actual hardware keylogger, and the ability to send our logged keystrokes out over the network to a remote host, all from within SMM. So the system management mode memory space is called SMRAM. SMRAM contains the CPU state at the point of entry into SMM. It also contains the SMM handler's code, data, and stack. The chipset documentation actually defines 3 locations for SMM. These include the compatible location, which is also the default, which is located from A0000 up to BFFFF. This location, incidentally, is also the legacy video range. 2 additional locations are the HSEG and the TSEG locations, which are designed to provide a larger write-back cacheable memory space for SMM. We've looked at a bunch of systems, actually, during the course of this project, and we've seen systems that use all three of these different modes. The most common ones seem to actually be the compatible and the HSEG. We've only seen one system using TSEG. The base address of the SMRAM space is actually contained in an internal processor register, which is called SMBase. So this diagram shows the location and layout of a compatible SMRAM region on a 32-bit system. As you can see, the region, because it is the compatible region, extends from A000 up to BFFF, and SMBase points to the beginning of that region. The SMI handler is also by default located at SMBase plus 8000, and the state save area is located at SMBase plus FFFF. These are all the default locations for the handler and the state save area. So if you look in the Intel manual, it defines the SMRAM State Save Map. This shows what is, when we enter SMM, what does the CPU store for us so that it can restore when we exit later on. As it ends up, most of the registers are actually preserved across an entry into SMM. These include most of the control registers, the flags register, the instruction pointer, the stack pointer, most of the general purpose registers, 2 of the debug registers, and then all of the segment registers, along with a few other miscellaneous fields. So we said earlier that one of the reasons that SMM might be an attractive location for a rootkit is the fact that there's an isolated memory space. As it ends up, the SMRAM memory space isolation is actually enforced by the memory host controller. There's actually a couple registers in the chipset that actually control the access to SMM from non-SMM modes. One of these is the dopen, is a bit called dopen, which is in a system management mode control register, which is, I believe, defined in the MCH documentation for the chipset. So what dopen does is it controls the visibility of SMM memory from inside and outside system management mode. So when a memory access to SMM actually occurs, the MCH looks at that address on the bus and also the value of the system management mode control register and the dopen bit and also another bit called dlock, and looks at it and sees if that access is allowed. If the access is allowed, then that memory access goes through and you're able to read the actual contents of SMRAM. If the MCH determines that that access is not allowed, then it reroutes the memory access to the VGA frame buffer region. So SMM is entered in response to an SMI, or a system management mode interrupt. On an SMI, the processor state is saved to SMRAM space, and control is transferred to the entry point of the handler, which, as we mentioned, is located by default at SMBase plus 8000. The handler returns control after it's finished executing by executing a resume instruction, which causes the processor to restore the state that was stored in the state save area back into the CPU registers and hand control back to the code that was originally interrupted by the SMI. So we kind of break our implementation down into 3 subsections. The first one being how do we get the rootkit in there, the installation. Then we talk about how we implement a keylogger at the chipset level without having to make any changes to the interrupt descriptor table to intercept interrupts. And then talk about how we integrated our deeper door code into our SMM rootkit. So installing a rootkit essentially consists of 3 steps: opening SMRAM for writing in the new handler, and then finally locking SMRAM. Before we talk about the details of those things, I need to review the PCI configuration space, because the registers that we need to access are located on the chipset as opposed to in the processor. So we need to know how to access the chipset. So basically, each device on the PCI bus has a configuration space. They're addressed by a triplet, which is a bus, device, and a function number. Each device in the PCI configuration space has a header, which you can see the layout of a standard header over on the right. We can also read and write configuration space by programming two chipset registers, the configuration address register and the configuration data register. So the actual device that we're interested in is not a typical device like you would think of like a network card or an external card. The device that we're interested in is actually the DRAM controller. So right here is an image of the configuration space for the DRAM controller as it's defined in the chipset documentation. The two registers that we're really interested in are down there at the bottom at offset 9D and 9E. And that's the System Management RAM Control Register and the Extended System Management Mode RAM Control Register. So we're going to access those two registers by reading and writing the configuration address register and the configuration data register. We can think of the PCI configuration space as a giant window, but a huge window of memory that we can only access 32 bits of at a time. So in order to specify which 32 bits we actually want to access, we have to specify that in the configuration address register, which, as you can see, the layout includes the bus, device, function, and register numbers for the configuration space that you want to access. This register is located on port CF8 and is accessible using standard port I/O. Once you've set the configuration address register with the location you want to read or write, then you actually do the read or write by using the configuration data register. The configuration data register is located at port CFC and is also accessible using standard port I/O, like assembly in and out instructions. So the System Management Mode RAM Control Register, or SRAM-C, is the register used to control the visibility and accessibility of SMRAM. The layout and location of this register is chipset specific. On most of the systems we've looked at, it seems to be located at an offset of 9D, but we have found a couple of exceptions to that, so it does seem to be chipset specific. We read and write the SRAM-C register using those two PCI configuration space registers that we just talked about. The main bits that we're interested in this register are the dopen bit, the dclose bit, and the dlock bit, particularly the dopen and the dlock. So here's like just a little snippet of code that shows how you might read the SMRAM register. We move the configuration space address location into EAX, which is the location of the SRAM register in the chipset. We move CF8 into DX, that's our configuration address register, execute an out to write to the configuration address register and set it up for the SRAM register. And then we load CFC into DX, which is our configuration data register, execute an in, and EAX at this point should contain the value of the SRAM control register. So specifically, the bit dopen controls whether or not SRAM is visible from non-SMM processor modes. So if dopen is set, SMM is readable and writable from outside SMM, which means that from Windows we can write into SMM and like install a new handler. If dopen is clear, the MCH will reroute the accesses to the frame buffer, like we saw in that diagram before. In order to install the new handler, therefore, the rootkit must set the dopen bit. So that is one of the first steps. The other bit that we have to worry about is the dlock bit, because the value of dlock will actually determine whether or not we can set the dopen bit. If dlock is set, the SRAM control register will be read-only, and you will no longer be able to write or read from the SMRAM space. Unfortunately, the only documented way to clear D-lock is via reset. Nevertheless, in our research, we discovered that a lot of systems still remain vulnerable. It seems like newer systems have newer BIOSes that have actually set the D-lock. But a lot of older systems still, are running older BIOSes that would remain vulnerable to modifications to SMRAM. So installing the rootkit, there's kind of 3 steps here. We either need to replace or hook the existing SMM handler. So assuming that our system is not locked, we can make SMRAM visible from protected mode by setting that the open bit in the SMRAM register. At that point, we are going to be able to copy our code in because SMRAM will be accessible to us. And once we have our rootkit copied in, then we will clear the deopen bit and set the delock bit so that detection software can't scan SMM and read out the rootkit code and, test for a signature or anything like that. So on this box that we're going to demo on a little bit later, this is a dump of the original SMM handler, the very, very beginning of it. So we dumped out the handler memory, disassembled it in IDA, and just took a look at it. And this is just the first few lines of it. You can see the first thing it does a jump to an offset of 5 from the beginning of the handler. So it jumps down and it clears the direction flag. Next thing it does is it loads the segment registers. It sets up a stack for the handler. Loads the IDT and reads the current value from the configuration address register to see where it points to in the PCI configuration space. And then it does a whole bunch of other stuff, but we don't really care because we're going to overwrite it anyway. So we overwrite the handler with our new handler, and then we redumped it and redisassembled it in IDA, and this is what it looks like now, right at the beginning here. First thing we do, we clear the interrupt flag, which is actually kind of redundant, but maybe just a throwback of of force of habit. And then the next thing we do is we load the data segment register with the base of SMRAM. We load the ES segment register, the stack segment register. Basically, we load all the segment registers with the base of SMRAM. If you notice in there, you see these weird little DB66, which are kind of like peppered in with our code. Those are actually override prefixes because normally you can only access 16 bits in SMM, but if you use the override prefix, you can access the full 32-bit linear address space. So we do that, set up our stack. We access the PM base register because after we finish executing an SMM, there's a bit in the chipset that we need to set, so indicating that we have reached the end of an SMI, and it has to be set for the processor to be able to respond to further SMIs after we leave the handler. So it's an offset from PM base, so we have to locate PM base. And this just goes on for, maybe a few more hundred to a couple thousand lines that we're not going to go over in more detail. But it's kind of simple in theory, I guess, hooking the handler or installing a new handler, but there can be some complicating factors because we tried this out on several different systems, and we found different problems on each one. For one, like overriding the handler can cause system instability. You can't just blindly overwrite it like we first thought we could because we were working on desktops primarily. And as it ends up, desktops don't really use SMM that much, probably because they don't do as much power management as laptops do. But when we started trying to get it to work on a laptop, we realized that we were getting freezes and lockups all the time, and eventually made the connection that laptops tend to have more aggressive power management and are probably actually using SMM, and we can't just blindly overwrite it. So at that point, we realized that the better approach is to actually hook it. So this also introduced some difficulties because on a couple of systems we looked at, we found it difficult to find space to store the new handler because SMRAM is of a limited size. And, depending upon the BIOS manufacturer, because the BIOS is usually what sets up the SMM handler, would kind of depend on, what its structure was and how big it was. And sometimes there was enough space, sometimes there wasn't. So that could kind of complicate things. But once we got the handler installed, we faced a few challenges to the implementation of our chipset level keylogger, because we wanted to be able to log keystrokes. First thing we had to do, we had to be able to intercept the keyboard interrupt from within SMM. We can't do this in the traditional manner because we don't have access to the protected mode IDT. We must also be able to sniff the keystrokes at a low level, and then finally, we have to make sure that the keyboard continues to work normally, because it wouldn't do us any good if we broke the keyboard. So in order to intercept the keyboard interrupt, you have to know a little bit about the APIC architecture. Basically, there's two components in the APIC. There's an IO APIC and there's a local APIC. The IO APIC is located on the motherboard. Usually there's one IO APIC per peripheral bus. The primary job of the IO APIC is to route interrupts from the bus to one or more local APICs, which will depend on how many CPUs are installed on the system. So the local APICs are integrated into the CPUs. There's one local APIC per CPU. The local APIC, the primary job of the local APIC is to receive interrupts that have been routed to it from the IO APIC and then forward them on to the CPU. When the CPU receives the interrupt, this is what most people are familiar with. The processor looks up the handler in a data structure called the interrupt descriptor table and calls the handler. So normal rootkits intercept interrupts by replacing the handler in the IDT. Of course, looking for abnormal pointers in the IDT is a heuristic that a rootkit may be installed, and it's a heuristic that quite a few detectors try to employ. Incidentally, this is also one of the drawbacks of our deeper door rootkit that we talked about. We needed to intercept an interrupted indicated frame arrival. So using this technique, by moving all our code into SMM, we can actually get around that. Because SMM rootkits can't make changes to the protected mode IDT. I mean, it wouldn't do it any good. And more than that, they really don't need to. Because the SMM rootkit can intercept interrupts much, much earlier before they even get to the processor by affecting their routing in the IO APIC. So the IO APIC defines a data structure called the Redirection Table. This is the data structure that's used for routing interrupts. The Redirection Table contains an entry for each interrupt pin and is used to specify the routing information, which includes the destination, the vector, and the delivery mode for the interrupt. Most interrupts tend to use the fixed delivery mode. When the IO APIC receives the interrupt, it gets forwarded onto the local APICs and then onto the CPU. However, for our keyboard interrupt, we want to receive notification in our SMM handler, so we can actually change the delivery mode for the keyboard IRQ in the chipset from a normal fixed mode to an SMI. So once we've made this change, whenever the user presses a key, it'll cause an SMI to be generated by the IO APIC, which will cause our SMM handler to be called, and at which point we can extract the keystrokes from the keyboard data buffer. After extracting our data, though, we need to be able to deliver the interrupt to the CPU. The keyboard has to continue to function normally, and the OS has to, can't know that something has been subverted earlier in the process. So in order to do this, in order to forward the keyboard interrupt, we can use the local APIC. The local APIC has the ability to issue interprocessor interrupts. It defines something called an interrupt command register. When you write to the interrupt command register, the LAPIC generates an interprocessor interrupt and sends that message out over the system bus. So basically, from our SMM handler, once we've extracted the keyboard data, we can reissue the keyboard interrupt using the LAPIC and send it onto the CPU ourselves. So this diagram kind of illustrates this whole idea of interrupt redirection. So on the top level there, the user presses a key press. Normally, it goes through the I/O APIC. The I/O APIC looks up the IRQ, sees that it's vector 93, creates a message on the bus, and sends it to the local APIC. The local APIC forwards it to the CPU, which looks up vector 93 in the IDT and goes ahead and calls it, which in this case would be the OS interrupt handler for the keyboard. In our case, we changed the keyboard IRQ to SMI in the redirection table. So when the user presses a key press, the I/O APIC immediately generates an SMI before ever sending it to the local APICs to the local APIC in the normal manner. So our SMM handler gets invoked. At this point, we can extract the keystrokes, and then we create our own interprocessor interrupt and through the local APIC and reissue it onto the processor where it's looked up normally again in the IDT. Because we can also specify the delivery mode. So we just create a message on the bus that says, we want to fix delivery mode now. We want it to be vector 93 and send it out, and the CPU will go ahead and look that up in the IDT like it would normally. So that's basically how the keylogger portion works in SMM. We also added network backdoor functionality into our rootkit. If you saw our last talk, you have a better idea about how all that works, but I'm going to go over it really, really briefly in a few slides right here. As it ends up, sending data out ends up being really easy. We just need to write a few registers on the card, which are incidentally also located in the PCI configuration space. We developed our backdoor for the Intel 8255X chipset. It was tested on the Intel Pro 100B and Pro 100S cards, but there's quite a few other cards that are backwards compatible with this chipset. There's also open documentation. Everything we've developed was developed using freely available documentation that you can download off of the web. So if you want more details, you can see our deeper door talk and slides. But just to briefly recap, the control and status registers are the registers that exist on the LAN controller that are used for accessing data structures that control the card. We can access the control and status registers for the LAN controller using either port I/O or memory. The CSR also holds what's called a status control block. This is probably the most important data structure because it's the primary mechanism for communication between the 8255X controller and the host CPU. So here's the diagram there, shows what the SCB looks like. There's 3 components to it. There's a command word, a status word, and a general pointer. We can send commands to the device by writing the command word. We can check the status of the device, like the causes of interrupts or error conditions, by reading the status word. And then the general pointer value depends upon what type of command we're sending. So if we're going to transmit a packet, the general pointer points to a linked list of transmit command blocks in memory. So here's the general steps for sending data out. Ends up being really easy. It doesn't take a whole lot of code. The first thing we do in our SMM handler, we build a transmit command block called a TCB. We're using what's called simplified mode on the card, which means that our data is going to directly follow the transmit command block data structure. We build a data packet, which in our case we're using UDP for simplicity. We check that the LAN controller is idle. There should be less of a problem. Some people noted there could be problems like with race conditions between us and the OS in the last talk. But SMM is non-preemptible, so we have exclusive control over all the hardware, as long as we're careful not to mess up any state that might already be existing there. So we check the LAN controller to make sure it's idle. We load the physical address of the transmit command block into the system control block. because remember I said the general pointer points to different data structures depending on the command. For transmit, it points to a list of transmit command blocks. This is followed by our UDP packet, as you can see in the diagram. And then finally, we just issue a CU start by writing CU start into the status control block command field. And that just causes the LAN controller to go ahead and send out the packet. So this is how we send out the keyboard data. We log the keystrokes into a buffer, and when the buffer becomes full, we just do these simple 5 steps and just send that keyboard information right out over the network. We also could access the hard disk controller from in there. We could easily, well, maybe not easily, but we could slowly exfiltrate someone's hard disk right out over the network, just as easily as exfiltrating their keyboard, although it could take quite a bit of work to get that working. So with that said, we'd like to kind of compare and contrast VMM and SMM rootkits, because there are some similarities, but also some critical differences between them. But they do both offer a similar level of control over the system, but in a different way. Virtualization rootkits, first of all, are themselves somewhat hardware dependent because they need Intel or AMD virtualization support. This limits the virtualization rootkits to newer systems, mostly 2006 or younger. In contrast, the SMM rootkits need to have the SMRAM unlocked. Incidentally, the older systems appear vulnerable to having their SMRAM remaining unlocked. From our research, it looked like most systems before 2005 and younger tended to still be unlocked. So we kind of have a nice, sort of a nice complement here with the VMM and the SMM rootkit. You know, the newer systems can support the VMM rootkit, but they tend to be locked to an SMM rootkit. The older systems don't have virtualization, but yet their system management mode is often still unlocked. So using both of these techniques, we can target a much larger number of systems with an operating independent piece of malware. The operating environments tend to be very different between the two. The VMM rootkit tends to operate in protected mode with paging. Well, by definition, it actually operates in protected mode with paging. The SMM rootkit, though, operates in 16-bit mode, which is more similar to real mode and doesn't use paging. Both rootkits are OS independent. Both are able to hide their memory footprint. The virtualization rootkit has to use memory virtualization, which can incur a performance penalty because memory virtualization can be really slow unless there's also support for hardware-assisted memory virtualization. Whereas the SMM rootkit won't really have that problem with performance or needing hardware memory virtualization because it hides its memory footprint by default, just because of the way the MCH handles accesses to that SMRAM space. Both rootkits can exert a high degree of control over the system. Both can implement most types of rootkit functionality that you would want because they can both interact with the underlying hardware at a low level without alerting any kind of a host OS that might be running above. But the VMM rootkit controls the system in a different manner. It tends to intercept more CPU-type events like processor interrupts, debug and control register reads and writes, or accesses to privileged instructions, where the SMM rootkit is limited to control over the chipset and doesn't really have that much control over events on the processor. But as we saw, we can still exert quite a bit of control over hardware. We showed the network card and the keyboard. We can reroute their IRQs in the APIC, for example. And there's probably some other chipset data structures that we could play around with. Probably the biggest limitation to our rootkit is, of course, that DLock bit. There's not a documented way of unlocking DLock. Also, the fact is that we are chipset and hardware dependent, so that's another limitation. This type of rootkit is probably still best suited to a targeted type of attack, where you have some knowledge of your adversary's hardware. Because if you make a mistake on this kind of code, you're guaranteed to hose the box. I mean, you know, there's not going to be any recovery. So if you need to make sure it works, you're going to probably have to have some kind of knowledge of the hardware that your target's running. Handler also has to be written in assembly. There is no OS driver or debugging support. Debugging this thing is actually a big nightmare. And finally, we're not able to survive a reboot because we're not a persistent rootkit. We could probably work on that some, but we don't have any way to survive a reboot at the moment. So let's talk about defense. We can probably get some ideas for defense by looking at some of the proposed detections for the SMM rootkits. One of these is looking at TLB and cache discrepancies. Unfortunately, this isn't particularly useful for an SMM rootkit, mainly because the SMM rootkit operates in an environment where paging is not enabled and the default memory space is non-cached. So there won't be any effects on the TLB or the cache. Some people might suggest, you know, well, what about moving detection off the CPU to another device that has access to physical memory? Well, this won't work because the MCH arbitrates all external device communication on the bus. So even a peripheral PCI card that might try to access physical memory will ultimately have to go through the MCH, which is sort of the gatekeeper for that SMRAM region. What about timing abnormalities? As it ends up, the timestamp counter does appear to be updated during an SMI, but it's also likely possible for an SMM rootkit to cheat in a similar manner to a SMM rootkit. Finally, we'd like to note that rootkit detection, as far as heuristics go, has focused on detecting changes to a lot of processor-specific data structures or OS-specific data structures like the interrupt descriptor table or the system service table. Well, I think maybe this SMM rootkit brings awareness that there are also chipset level data structures that can be subverted, and one of those is the IO redirection table. So adding some heuristics for checking these kind of data structures might be a worthwhile addition to rootkit detection. Nevertheless, a keyboard interrupt that's been routed to an SMI can't really be considered sufficient as a measure of compromise. And the reason for this is that keyboard interrupt to SMI routing has been used to legitimately provide legacy keyboard and mouse support for USB devices. There's actually a whole article on this over at the MSDN on Microsoft. So there are legitimate uses for routing interrupts to SMI. But it could still be, used as a flag. Probably the best defense is not real exciting. Duflo's recommendation that DLock be set is probably still the best method to ensure an SMM rootkit can't be installed. As we said, many newer systems have actually locked the SPIT in the BIOS, but many older systems remain unlocked. Also, these systems don't support virtualization. So on these systems, the SMM rootkit could be a viable option. Of course, we might be able to work around, the locked space by, reflashing the BIOS, which will make things even more hardware dependent, or even flashing the boot ROM of an installed PCI peripheral card. But both of these things would make our implementation a lot more hardware dependent. And almost guarantee that you'd have to have some knowledge of the hardware configuration that you were going to attack. So at this point, I'm going to turn it over to Sean. He's going to do our demo.
Hi, everybody. We're going to try another demo. Okay, once again, we have two machines. Oh, sorry, hold on. So we have our target machine over here, the big target on it. And then in this case, we don't really have a command and control machine, but we have a machine that's going to sit around and just listen for data over the network because the SMM rootkit is going to log stuff and send it out. So we'll just send it over to this remote guy. So here we're just going to open up Network Monitor. Start a capture tab, And the data will be coming out. This is 101, and this is 103. So we have a filter which is going to listen for the source address of 103 in UDP. So apply that. Start it up. And then we should be good to go over there. So on the target, we're going to give you an idea of all the stuff we just said. I'll run down through it. Go ahead and find and start it up. And we don't need driver loader anymore. So if we take a look at what happens here in the debug output, so we have just some driver routines, and then here's the SRAM control register. So when we first look at it, so we have 9C, 9D, 9E, and 9F. So the 0A is, the 0A is the 9D offset, and that's the SMRAM control register. The 0 means that it's neither open, locked, or closed. And we need to make it open. So we'll go ahead and set the open bit, which is bit 0, 1, 2, 3, 4, 5, 6. So now it's 0A to 4A. So now that the SMRAM space is open, we're good to go and keep going on. Here's where we just allocate some memory and build a packet with some empty data where we're going to log the keys and then send it out once the buffer's full. In this case, we have it set to 16 bytes, just so we don't have to wait all day and type a paragraph. So every 16 bytes, it should go ahead and package up a packet and interface with the LAN controller to send that out over the network. These are just some registers, like this is the physical address of the memory map base, and that's how we're interacting with the LAN controller's control status register. And these are just some more things. This is the that status control block, which actually has the command word. This is the register you'll write to say, okay, command unit start, issue a command unit start command to go ahead and send the packet. The receive unit's in there. And then this is the general pointer register. That's its physical address. So when you issue the command start, before you do that, you'll load this up with the physical address. So we'll write this physical address into this command, into the general pointer, and then issue a command unit start, and that'll send the packet. So since we're hooking at the IO APIC level, we have to go down to the APIC and take a look at it. So if you look here, here's the original entry for IRQ1. Now these redirection table entries are actually 64 bits, so this is the low D word. It's the one that has the vector in the delivery mode. So the vector here is 9.3. So that would be the IDT vector for once it gets to the local CPU. And then this 9 incorporates 1 bit plus the delivery mode. Right now it's set for fixed. So we don't want fixed. We're going to change that to SMI. And per the Intel documentation, it says SMI is unsupported, but if you use it for compatibility reasons, just go ahead and set the vector to 0. So we did that. Again, we need to read PM base because most of the registers that have to do with SMI are at an offset from PM base. So we get PM base, and then we just go ahead and look at some of these status registers, control enable. We're just making sure that some bits that we need set are set, like global SMI enable. If that's not set, you can't generate SMIs for any event in the system at all. So we verify those are the way we want them, and the into SMI bit is set. And now we get to the interesting part, the SMM handler memory. So this is the original. This is just the first few bytes of the original. Let's see if I can make that bigger. So these are just some of the first few bytes of the original handler. And I believe we had the slide that was the IDA. So you can see this EA first byte is this long jump. And it went to A0008005, which was 5 bytes forward. And then it just did all this other stuff. The reason it does the long jump, by the way, is because when you first get in and you don't have a stack set up, you can't push and pop. I mean, you can, but you don't know where it's at. So executing a long jump will actually set the CS register, And then from there on, you can just move it into the other data segments. In our SMM handler, it's kind of low down and dirty. We don't even bother that. I just hard-coded A000 in there and moved them on into the segment registers. So either way, it's all the same effect. So after we write our SMM handler code, here's the output. And you can see that it's changed. This is the offset 8000 from the start at compatible space is A0000, and then the default location for the handler is 8. So now we've changed the long jump to this FA, which I think is like the CLI, and then this 66, which is the add operand override prefix, on and on. So that's the output that we saw on the other slide. So now we're good to go. We have installed, and in this case we're not, we pretty much clobbered the existing one. We didn't bother to try and inline hook it or anything. So fortunately for the desktops, they don't use SMM much, as long as you don't try and hibernate or shut down or restart. But you can just overcome that by hooking it. Okay, so that's just a rundown of how to get it installed. So we should be up and running. So we can just pull up something like Notepad. And the idea is here, we start typing, and we'll clear this output over here so we can see a packet should show up. So it should be 16 bytes. And right now, when the interrupt is generated and it's redirected to SMI, we're not doing a whole lot. We're checking to see if there was a key press. We're checking to see if it was a key make, which means down as opposed to a key break, which is up. So if it's a key press, if it's a press down, then we look at the scan code, and if it's like a printable ASCII, I think we're filtering for like, just the main body of the keyboard. So if we start hitting them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So on the next one, we should get a packet over here on this machine. So we hit A, and sure enough, every 16, it will fill the buffer up with the characters, and when it hits, it keeps a timer. So when it hits 16, it'll say, okay, I'm going to go ahead and package that up, send it out over the network, and reset the counter. So if we look over here, there's our packet with all the A's. And that'll occur every 16 bytes. So if we go down here, and I mean, if you want to see B's, you see B. Now you get another packet with the B's. And interestingly enough, you have to keep it kind of short and sweet, because when you're in SMM, the whole system is basically paused. So you have to be pretty fast in there. One thing we were able to do, we were afraid, well, maybe it's too much code and it's going to slow the system down, and the user will notice that they hit their keys and they show up a couple seconds later. But it's actually possible to do all the things I mentioned, check if it's key press, check if it's down, filter it for printable ASCII, put it in the packet, check the timer, send out the packet, and we can do that at the type mac rate. So you'll see the packets over here on this machine just full of C's, just showing up at the same rate. So it doesn't appear to be too much of a noticeable overhead, because it doesn't lag behind the typematic rate. So that's a good thing. So the question is, can it get out past the network? And in this, I don't think we have. Let's see. I forgot to check before. Okay, well, we happen to have Windows Firewall running. It's on and it's not allowing exceptions. So that doesn't seem to me to matter much here, because the keylogging is occurring and the packets are being sent out without much of a problem. We can try something like Zone Alarm, which has a little bit more hardy outbound filtering and locking down of all applications. Real quickly, if we look at the zone we're in, it's the internet zone, and the internet zone's high, the other zone's high. We can go ahead and full lock everything and then see if it keeps sending out. if you were here for the deeper door, you saw that it didn't matter much. We're still getting packets sent out over here. So we're still getting our keylog data, and it's still being sent out to the remote machine. So something like Windows Firewall or Zone Alarm, they weren't really designed to catch this type of stuff, so it's not surprising that they don't. So then we're interested in seeing, well, since we have this rootkit installed, will some of the popular detectors find it? And scouring the internet, we saw this Gmer and this rootkit on Hooker. Gmer seems to be pretty comprehensive in what it does. So we can always open it right up and start a scan. Now one thing, and these are all the things that Gmer will scan. We don't really expect it to find anything, however, because we don't put any hooks in the system service descriptor table. We're not hooking the import address table or anything like that. This is somebody trying to get out. We're not really hooking anything in. The only thing that Gmer will find is it will see that the driver, the module's loaded because we simply haven't uninstalled, which you could easily do, just unload the driver. And it will find the entry in the registry. It'll find it as a service because we didn't remove the entry from the registry. Because we're using OSR loader, and OSR loader puts all that in. But there's other ways to install driver code and kernels that, are not going to leave that trace behind. And because everything's in the SMM, we don't really need to leave the driver sitting around because we just put everything's in SMM memory. So we don't even have to allocate anything and not free it and leave. We can just pretty much uninstall and go away, and then we're not going to show up in the module list or the service entries. And it's just not going to find anything, out of the ordinary because we're not hooking anything. And I don't think Gmer is checking the IO APIC redirection table. So the whole time this is going on, we can just happily send packets out. And Gmer will find a lot, but it won't find this. And the other one we saw is Rootkit on Hooker. It's pretty comprehensive too. It looks to be on par with Gmer and pretty much search all the same stuff. But again, it's not going to find anything hooked there. It's not going to find any code hooks. It will just see it as it'll show up in the drivers list down here somewhere. So, but that's just because it's not uninstalled and we haven't removed it from the registry. So pretty much it doesn't look like it's very detectable. It's not receiving anything in, and since we're just logging keys along and sending them out, I don't know what else to say. There it is. Keylogging. Uninstall. So we have a little bit of time. So if there's any questions, we'd be happy to try and answer them. Yes. Oh, we're supposed to tell you that there's a microphone in the middle, I was told. So because it's all being recorded to line up. Yes.
Did any of the related work release code for locking down the SMM, or are you guys going to release code? Because it looks like you said it's trivial to stop it just by locking down. So are you going to release that?
Well, I mean, there's nothing to really release. It's like 3 lines of assembly. It was
right,
like,
exactly.
It's released on that slide. You just set the delock bit instead of the deopen bit, and you're done.
Right.
So that's in Duflo's paper and everybody else.
Hi, I have just one comment. Actually, I have good news for you because it's actually not true that present systems cannot be, well, the SMM handlers of present systems cannot be overwritten. And actually, incidentally, tomorrow when we will be discussing how to compromise Zen that is protected by VTD, we're going to discuss one bug in recent Intel motherboard that also allows to overwrite SMM handler on the fly, even if it is delocked.
Yeah.
So this still works on today's systems.
Well, that's the official word from the Intel manual, is that only a reset will unlock delock.
Hello. I was wondering if you could touch a little bit on how you went about debugging this. Did you have to resort to hardware debuggers, or did you have to come up with some other solution?
We wrote out over the serial port. We wrote some code in the SMM handler that can output strings over the serial port. So we were able to output simple registers and stuff for debugging.
Yeah, that was the easiest and quickest way to get a lot of data out that was like human readable.
Yeah, we don't have an ICE, so that was like the next best thing.
Since you have access to the entire memory space, you can also just write, you can just allocate a page and write variables into it or whatever you want, and then you can see them from the OS itself. But over the serial port's the easiest way, probably. Any other questions? Alrighty, no more questions. Thank you for attending.